Welcome to my free CCNA training series. This video will be covering the topic of subnetting. Having a firm grasp on the basic IP addressing and network fundamentals is required before watching this tutorial. We will start by answering a few quick questions regarding subnetting. What is subnetting? It is splitting one network into two or more networks through changing the value of the subnet mask. Why do we need subnetting? Subnetting helps conserve the number of available global or public IP addresses by separating large chunks of IP addresses into the smallest subnet possible. This also provides security by not forcing different parties to share a pool of IP addresses. A real-life example of subnetting is the network connection between your modem and the ISP's network device at your neighborhood's telco station. This connection usually is subnetted to allow for as few available hosts as possible, so it is usually a 30-bit mask, which has IP addresses for two hosts. Here is a summary of subnetting basic concepts before we begin subnetting. A subnet mask is made up of 4 octets equaling 32 bits. There are 8 bits per octet, and each bit is a binary number. The higher the subnet mask value will mean fewer IP addresses per subnet, but more available subnets will be created. The lower the subnet mask, the more IP addresses per subnet, with fewer subnets available. This table displays the available subnet values for the 4th octet. Below each value is the corresponding bit mask value. Below each bit mask value is its block size. A block size is the total amount of IP addresses per subnet. Notice how if you add a block size to its corresponding mask, it will equal 256. Below the block size row is the host row. The host row shows the corresponding amount of IP addresses available per subnet. Take note of how the amount of hosts is always 2 less than the block size. This is because each subnet needs a network and broadcast address. Below the amount of hosts row is the amount of subnets available when that mask value is applied. Take notice of how you can multiply the block size by the amount of subnets available, and it will equal 256. Below the slide are formulas used to subnet. As you can see, there are formulas to find any variable in the chart based on knowing the corresponding value required. It would be wise to copy everything down on the slide for later use in this tutorial, for your certification exam, and also for use in real-life subnetting situations. By use of these formulas, you can take any subnetting variable and quickly convert it to any of their other needed values necessary to implement subnetting on a network. Now we will go over what we have just covered in some practical examples as a way to make sense of the subnetting concepts we have just covered. We are first asked how many host addresses does a 192.168.0.1/25 network provide. In order to find the amount of available IP addresses, we need to first find the block size. To find the block size of the subnet, first divide the mask by 8. Since there are 8 bits per octet, every time 8 goes into the bit mask, one filled octet with a value of 255 is found. And it is not the octet we need to find the mask for. We have 3 with a remainder of 1, so we know our subnet mask is in the 4th octet. Now we take the 1 bit remaining and we find the first bit's corresponding value in the chart to find out the block size. The block size is 128, meaning 2 subnets with IP ranges of 0 to 127 and from 128 to 255. Once you have a block size, subtract 2 and you will have your host block of IP addresses per network, starting with 1 through 126 for the list for the first subnet and 129 through 254 on the second subnet. Now on to more subnetting exercises to show a couple of scenarios you could be presented with on test day. You need a subnet to support 64 hosts while wasting as few IP addresses as possible. What subnet mask will meet this requirement? The first step is always to remember the network and broadcast addresses, so add 2 to 64 to get 66. Now that we have our minimum block size requirement, we can look at our bit chart and find the smallest value, or block size, that will be able to support 66 addresses. 128 is the smallest value capable of providing enough IP addresses. So now I found our block size, which is 128. If we subtract 2 for the network and broadcast to find out how many host addresses, we get 126. And finally, we need a subnet mask to configure our network interfaces with. So we take 256 minus the block size of 128 to get 128 for our subnet mask. The next subnetting problem asks us how many hosts can a 192.168.1.0/27 subnet support. We'll first take the bit mask and divide by 3 to find out our octet. We hold on to the remaining 3 and find the third value on the chart from left to right, which is 32. Since we now know our block size, we can then subtract 2 for our network and broadcast address, and we will get 30 for our block of host IP addresses. And finally, we will have one more subnetting exercise that will show how to subnet for a larger host address size of 254. We are asked how many hosts can a 10.0.0.0/23 subnet support. We will start by dividing by 8 to get our remainder of bits used by the mask. Notice how 8 only goes into 23 2 times. This is because we are using the third instead of the fourth octet as our mask placement position. With the remainder of 7, we can count our bits out to get a block size of 2. This may not seem usable if you subtract the network and broadcast address for your host size, since you get 0 hosts. The trick with using a subnet in the third octet is to multiply each bit by the mask by 256, since you have the fourth octet full of IP addresses that are usable. So multiply 2 by 256 before removing the network and broadcast address, and you will receive 510 as your total amount of usable host addresses. In conclusion, this tutorial has covered how to perform subnetting calculations. Happy subnetting!